why the
especially because
is it's chill.
Alright, so welcome everyone. We're gonna get started. So this is the Tools and Technology seminar series. I see a few new faces, which is awesome. So for those of you who've not been here before, this is a weekly seminar series at this time, and it's a little different than standard seminar series, as the title suggests. It focuses on tools, technologies, methodologies. Sometimes these are still in development. Other times they are recently published or recently completed, or maybe you don't have anything to do with the actual creation of the tool, but it's just a resource that someone uses and likes and thinks would be of interest to others. So there's a sign-in sheet that I just sent around. Hopefully it can circulate, and if everyone can sign in, that would be great. It just gives us information to help with the pizza. And so I'm going to turn this over to our speaker. Today we have Kerby Shedden, who is a professor of both statistics and biostatistics, and also director of CSCAR. And if you're not familiar with CSCAR, it now stands for Consulting for Stats, or Statistics, Computing, and Analytics Research.
Thanks, Marcy.
It's enough.
It used to stand for
Center for Statistical
Consultation and Research. We managed to change the name without changing the acronym. Okay, let's see. I need to not be in front of there. Okay, thanks everyone for coming. So it's lunchtime, and people, at least who are here, are eating pizza. So I hope this can be informal. And I know I have more material here than I can possibly cover. So feel free to redirect me at some point if you feel like one aspect of this is more interesting or another aspect is less interesting. Then just tell me so, and I'll be happy to try to adapt. So this is a talk about tools and technology. It's actually a reworked version of a more substantive talk on the application area. So instead I decided to take that talk, or to meet the needs of this seminar series, I decided to take that talk and restructure it with a little bit more emphasis on the software and the techniques, but it's still presented sort of as a mix of a tech talk and a case study. Basically what I'm getting at here is an overview of some of the experiences I've had over the last year or so evaluating and implementing tools for analysis of large-scale and heterogeneous data, which is a hot topic all over the place right now, and I'm just one person trying to do something a little bit special and unique, and also trying to meet the needs of my collaborators. The tools and technologies I'll mainly be focusing on today were developed specifically to meet the needs of two collaborative projects I have on my plate right now. One is more relevant over here. It's an analysis of medical claims data in the context of health services research, specifically for cirrhosis, although we also have things going on now with heart failure and cancer. And the other project, which I'll just barely allude to at one point, is in transportation research, looking at data coming off of sensor-equipped vehicles. They're actually both MIDAS-sponsored projects, so they have that in common. So the way I want to organize this, and like I said, I'm happy to move quickly through parts that are either familiar or less interest to this particular group, is to start with a little bit of background about the motivating application in claims data analysis and health services research, and then move on to the two technical topics that we focused on. One is data layout optimization to facilitate person-centered analysis of large claims data sets, specifically in the context of this cirrhosis study. And then the next would be, well, I see a spelling error there, but the development of some new tools for streaming data processing to facilitate analysis of big data sets that can't fit into memory, and some data management and statistical tools that we've developed to make that feasible. And like I said, all of this is set in the context of one case study in particular, looking at trends in cirrhosis prevalence and the cost burden of cirrhosis. So this was done as part of a collaboration with Jessica Mellinger, who's a faculty member in gastroenterology. And she came into CSCAR actually about 3 years ago and asked if anyone there could help her do some analysis of this type of data. And it was supposed to take 3 months, and it took 3 years. And it led to the development of a bunch of tools. And I'll say a little bit about why that is. There's some reasons for it. When we get there, we'll get there. Okay, so let me give you a little bit of background about claims data and EHR, because that's, again, the application setting here. So claims data in particular is sort of the poor sibling of the more hot topic, which is these days, which is EHR analysis. So claims data are electronic records that are collected in the process of healthcare delivery that are primarily intended to facilitate financial side of the operation. So They basically record all of the procedures and services that are provided to patients, and they are then used to collect money from the payers. So the flow of information here is typically that you go to see your doctor, you go to a provider organization, a clinic or a hospital, and then the provider organization uses claims to document what was done. The claims make their way back to payers, which is often health insurers, and then the payers supposedly pay, and then that's how the providers get effectively reimbursed for what they do. Claims have been around for quite a while. For many years, people were analyzing claims data. We have a couple of people at CSCAR who spend a lot of time on claims data, especially out of the VA and CMS, and it was never like really a high-profile topic until the health policy and the financial side of the health system became a really important topic in the last 10 years or so, and this area has gotten a lot more traction. It's always been a challenging computational and statistical task because there are lots of sources of measurement error and bias in claims data, and they've always been large. So it's always been challenging computationally. And they've been electronic since basically the beginning of modern history at least, and that makes them especially of interest for quantitative research. They cover large, broad populations, and so they're especially useful if you want to do research that can project out to a well-defined population, like in the case of the cirrhosis project I'll be talking about today, the so-called ESI, or employer-sponsored insurance population, which is more than half of the non-elderly U.S. population, the people who get their health care paid for through employer-sponsored insurance plan. Because the data sets are large, you can basically use weights to project them up and make statements about this population rather than just statements about a convenience sample, which is something that we often aspire to in statistics but don't always achieve. And an interesting thing about these data sets is, although from a finance point of view, it's primarily of interest that they capture the actual tangible services and procedures that are provided, we actually don't always care about those services and procedures so much, but because of the way the charging model works is that the provider organizations get reimbursed at a higher rate for treating complex cases, so therefore a bunch of contextual information about the patients is also entered into the claims data. So you get information about symptoms, comorbidities, and other health conditions that the patients have, which ultimately influence the reimbursement rate. And so we can use that to do things like identify when people first acquire a condition or disease, and if it's a chronic disease, we can use that to monitor the progress of the person as they usually progress through a sequence of ever-increasing disease stages. So that's what I'm referring to there as the contextual information. So to contrast that a little bit with electronic health records, which, like I said, is a very hot topic right now, health records, unlike claims, are primarily intended to facilitate care rather than to facilitate the financial side of the operation. They, for a long time, were primarily on paper rather than digital, although recently they've heavily moved in the direction of being digital. And unlike claims, it focuses as much, if not more, on the sort of overall condition of the patient rather than narrowly documenting what billable actions were performed. And they often are more heterogeneous in terms of the type of data they contain. They usually would be a mix of coded data and unstructured text. So, clinician notes is the canonical part of an EHR that people are struggling with nowadays. And I contrast that to claims data sets, which are usually coded, or in the case of the data we refer to today, it almost entirely consists of coded data. So we've got fields that have a defined set of values that they can hold, and so we're talking about processing these coded values. And I think on the next slide I have some examples of what I mean by that, if that's not clear. Yeah, I do. So a very well-known type of coded information that you encounter in a claims data set or a health records data set would be the so-called ICD codes. I'm sure everyone's heard of these before. ICD-9 now pretty much defunct, and things have moved on to ICD-10. But over the time span that we're dealing with for the cirrhosis project, we have mostly ICD-9 data and then some ICD-10 data crept in at the end. So the ICD system, I won't say a lot about it here. I'm not an expert, but it's a systematic way to code diseases, disorders, injuries, and other health conditions. And I think there's on the orders of many thousands, maybe up to around 10,000 or so distinct codes, although you don't encounter many of them very often. And so the idea is you have in any given claim a number of fields that the physician or the provider can fill in to document what what conditions and comorbidities and so on that the patient had, and these would take the form of ICD type codes. Those are for, like I said, symptoms, diseases, disorders, and so on. And then in terms of the procedures, what was actually done, we have other coding schemes like the so-called CPT and HCPCS codes. For example, I've just got the numbers up here that are relevant for the cirrhosis project, which is about livers, of course. So 47135 is the CPT code for liver transplant. And then there's another whole set of issues relating to drugs. So there are various ways of referring to and coding drugs. I'm not going to talk about drugs today at all, so I'll gloss over that here, but we do work with those codes a lot in other projects. Okay, in terms of working with this data, some of the challenges we encounter, as I mentioned before, there's issues with coding bias and errors. I mean, if a provider can simply enter the wrong code. These are people who have a lot going on, the physicians and nurses and so on who are entering the codes or providing the raw documentation that will ultimately turn into codes. So they may just make a mistake and enter the wrong code. But more importantly, there can be various biases. So because some of these codes lead to higher reimbursement rates, if a code leads to a patient being categorized as complex, there's a lot of pressure not to misstate or to lie per se, but to certainly to always enter codes that would ever be appropriate if they lead to a higher reimbursement rate for identifying a complex patient. And like I said before, procedures are generally well defined and well coded, but what we're more interested in are the health conditions, outcomes, symptoms, and so-called contextual information. And those are not always so well coded. There can be many codes that refer to the same thing or almost the same thing, and we have to deal with that in the analysis. I'll say a little bit more about that later. And also really important for us as analysts, if that's what you identify as, the data are not always very easy to get, although that's, at least at that's improved a lot in the last year, and I'll say why that is in a minute. You can't just call up an insurance company and expect them to share their data with you. So I'll tell you how that works in a minute. But the data someone has to pay quite a bit of money for researchers to get access to this data. There are some privacy concerns, although they're not necessarily as dominant here as they are in some other contexts, because the data, as I obtain them, as any analyst would obtain them, have been thoroughly scrubbed. So there's some disadvantages and challenges, and then on the upside, a big advantage is this, that essentially every time anyone interacts with the healthcare system is going to produce a claim. It's almost impossible to have any kind of formal interaction with the healthcare system and have it not lead to a claim. So it's very comprehensive in that sense, and as long as you can get your hands on the data, you can get very, very deep and broad portrait of the overall healthcare activity in large populations. Okay, so moving now a little bit more to the technical side of things, the major challenges for people who actually have to get their hands dirty with this type of data and do data processing, data management, and data analysis. So that in my somewhat limited experience, I've really only been working in this area for about 3 years. The typical workflow is that based on the analysis plan and the research goals of a project, you start off by needing to select a subset of people who would be deemed cases. So these are people who have the condition of interest. And that is not always a simple query. It can often be a fairly complex query. It's often not just do you have this code or not that defines whether or not, say, you have cirrhosis. We had to use a whole combination of factors to determine who really has the condition in exactly the way we wanted to define it. And so, but the fact is that the cases for most diseases, unless you're talking about something that's extremely prevalent, for most diseases you're talking about a small subset of the population. So on the one hand, when you hear that claims data sets are very large, so in a minute I'll tell you that we're dealing with many billions of records in the case of the claims data that I have access to here at things will very rapidly reduce in size when you select your cases, because the cases, like cirrhosis, is roughly 0.27 or so % of the non-elderly population. So you're talking about 0.27% of 10 billion records rather than something on that order itself. However, like I've indicated already, at least in terms of the people I'm working with, there's a major emphasis on using this data to project up to large populations. And so that means you're using survey-style statistics instead of classical sort of convenience sample types of statistical methods. And that means you can't simply ignore the rest of the data. So you actually have to aggregate some characteristics of the non-cases to properly adjust for biases in the convenience sample that we have relative to the population that we're targeting. So it's not simply a matter of immediately reducing the data down to 0.25% of the total. We actually have to engage with the entirety of the data, at least at some level. And then the really detailed analysis, of course, is restricted to the cases, but we're not simply ignoring the non-cases. These are also almost inevitably longitudinal style analyses, which makes the research much more relevant and interesting scientifically, but also makes the analysis somewhat more complex. So what we almost always end up doing is producing from the raw claims data what we call time logs. So time log would be basically like a longitudinal portrait of each subject from the point when you can first identify them as a case to the end of the line, whether they die or whether they drop off the insurance rolls or whether they just disappear. And that could contain hundreds, if even in some cases thousands, of events that would take place along that process as every time they go in to have a checkup, there'd be additional codes entered that would give you more information about what their status is at that point. If they get drugs filled, they go and have tests, and the lab test results come back. Even administrative information about like how their insurance plan coverage policy changes and so on. So again, even if you're talking about a so-called modest sample size in terms of, say, hundreds of thousands or up to 1 million people who have the disease of interest, then you easily have tens to hundreds, if not thousands, of records for each of those people. And that's on the data processing side. And then the final step, of course, for those of us like me who are in the business of doing statistical analysis, we want to apply, I'll call it advanced. It may not be like the most cutting-edge statistical methods out there, but they're advanced in the sense of the things that you wouldn't normally learn, say, in an undergraduate statistics class. And I have a laundry list of some of the techniques that we commonly use in this type of analysis there. I won't even read it. But certainly when you talk about data preparation and computation, it's not enough that you just prepare the data to the point where you can do something like a t-test. You know, the types of statistical methods we have to do, it's much beyond that. Okay, let me say a little bit about the data, and this is both information and also advertisement to some degree, because it deals with some data that is actually available here at Michigan, and I and other people would like to see more people using. So in the US as a whole, there are two large providers of commercial claims data sets that are used for research analysis, and those are the Truven and the OptumInsight data sets. So many of you have probably heard of OptumInsight. It's quite well known. Truven's a little bit less well known. These are large claims data sets that cover large fractions of this ESI population, the employer-sponsored insurance population. In addition to this, you can also look at claims data from non-ESI populations, such as we have a lot of people at who look at VA data, claims data from the Veterans Administration health system, and from CMS, the Center for Medicare and Medicaid Services, which would be Medicaid and Medicare. But that's not what I have experience with. So back on the ESI side, we have these two large data providers. So these are companies that sell data, and if you pay them quite a bit of money, on the orders of $50,000 or so, you can get access to the data for research purposes. And IHPI is a unit at the Institute for Health Policy Innovation, has several years ago licensed, well, for many years actually, maintained licenses to these two data sets, and the licenses are actually cover, as I'm told, the whole U. So in theory, anyone who's qualified and has a legitimate project can and always has been able to obtain these data for their research purposes. However, up until about 6 months ago, the data were locked away on some med school servers, and it was technically very difficult to actually access them. You would have to, at minimum, pay pretty high hourly fees for IHPI analysts to pull data for you, because they wouldn't let you just take the whole data and pull your subset yourself. They had to pull the subset for you, and then they would potentially fork over the subset. So you weren't paying for the data, but you would still be paying for the analyst time to pull the subset that you were interested in working with. So the new development from about 6 months ago was as part of the Data Science Initiative, which many of you have, I'm sure, have heard of, and Brian Athey is very involved with this, of course. We were able to convince IHPI, and they've checked that this was compatible with their licensing terms, to put the complete data for both Truven and OptumInsight on Turbo, which many of you would know is the large array of disks underlying Flux. So if you use Flux and you have data that's more or less static, data you don't need to constantly updating, it may well be on Turbo. So the Data Science Initiative is paying for the storage cost to have both Truven and OptumInsight on Turbo for at least the next couple of years. It's a long term, we'll see what happens, but for at least the next couple of years, that's what's happening. So these data suddenly became a lot more available. You don't have to burrow through the med school's firewall or get the IHP analyst to pull data for you. with the right permissions, it's not just there for the taking, but with the right permissions, you have to fill out some forms and talk to some people at IHPI and get them to approve your project. But they're generally pretty accommodating about that. Then you could get direct access to the data itself, or this hopefully doesn't sound like too much of an advertisement, but people at CSCAR are also able to pull the data for you. And that was the sort of incentive and motivation for us to look at better ways to interact with this data.
Those relational databases?
No, that's what I'm going to talk about next.
Oh, okay.
Well, not quite next, but I'll get there in a minute. Let me just say a little bit about just what MarketScan is. So MarketScan, it's actually easier to understand OptumInsight, the other of these two data sets that I've worked with last. So OptumInsight is simply a data dump from this one private insurer called United Health, which is a very large private insurer. They essentially take all their data, they very rigorously anonymize it, and there's all kinds of issues there that I won't get into today, and make a huge fraction of that information available to researchers. And that's basically what OptumInsight is. Truven is something, MarketScan, which is a product of this company called Truven, which was later bought by Thomson Reuters, which was later bought by IBM, is something very different and more interesting. So Truven is sort of the middle link between large companies and insurance companies. Like if GM wants to provide employer-sponsored insurance to their employees, rather than going directly to insurers and negotiating the terms of an agreement, they might contract with Truven, who would then assess GM's needs and look at the marketplace and try to find a good match. And then beyond that point, Truven would continue to serve as the middle link in the sense that all of the claims would flow from the provider organizations through Truven's servers to the primary insurers and back again. So, and Truven's job is actually to record and aggregate and analyze those claims to make sure that GM continues to get a good deal for their money. So that's their business, and as part of that business is sort of a small side business. They can take all that data that they collect, which covers many employers and many insurers, unlike United Health, which is just one insurer. And they can, again, anonymize it, sort of rectify the data, put it into a common scheme, and then sell that. And that's basically what MarketScan is. There's a lot more to it than what I just said, but that's basically at a high level, 30,000 feet, that's what MarketScan is. So it's interesting to researchers, especially those researchers who want to do population projections, because in theory, at least, one would hope that if you aggregate data from many different companies and many different insurers, you're getting a broader representation, maybe a more representative picture of the ESI population than you are through United Health, which is just one insurer. So of course there are strengths and limitations in terms of what each of these two data sets contain. MarketScan, for instance, doesn't contain data about race and ethnicity, so people who are interested in that side of the more social economic side of things, they go to Optum, because Optum does contain more detailed information about race and ethnicity. But if you're interested in the claims themselves, I think MarketScan and Optum are very comparable to each other. So I think I've said everything there that I need to say.
When a lot of times there's multiple plans people can choose from an employer. Do they link the people if they've changed insurance provider? So
that's a very, very complicated question. So there is some plan information if you're interested more in the economic side of things. Like if you want to look at so some people have, this is just the tip of the iceberg on that I've personally been involved with, is if you want to look at, in the past, not everyone had prescription drug coverage. So you may have had coverage for your office visits and procedures and hospitalizations and so on, but you actually had to pay for all of your prescription drugs yourself, and other people didn't. So there's a flag in there saying whether you did or you didn't. Long story short, they have to simplify and rectify this stuff, partly just to keep everyone sane, and partly to prevent de-identification. So they have to approximate and simplify. In reality, it's not a black and white thing whether you have prescription drug coverage or not. There's all kinds of nuances about which prescription drugs may be covered. So they simplify and approximate and give you sort of a rectified data set that in some sense covers all of these different plans, which in reality are different from each other in all kinds of complicated ways. And the issue of people dropping off and rejoining is another complexity. They try to, when people drop off and rejoin, like if you change jobs, they try to link through, but they fully acknowledge that they miss a lot of people. Many people will re-enter as a new person when they come back the second or third time. United Health and Optum are supposedly better at that because they are the insurer themselves. They're not missing a third link outside of the system, so they can use more information to do the linking. So these are issues with claims data. These are issues with these commercial claims data sets that have been scrubbed and made available to researchers. It's not immediately relevant for the technology side of what I'm talking about today. So here's a very concrete view of what MarketScan is. So MarketScan is delivered to you in the form of a bunch of SAS files. That's an answer to Jeff's earlier question, not as a relational database. And specifically what you get is you get about 8 or 10 different types of files covering 8 or 10 different types of data. So you get information about enrollment, information about inpatient visits, hospitalizations, information about outpatient visits. That's the big one. That's the one that most people are focused on. Facility and service charges, drugs, and the labs are very complicated. I haven't even looked at the lab data, but there is lab data, and that's big as well. I didn't even include it here. All told, at least without the lab data, there's something like 14 billion records and all the files combined. That's aggregating over 7 years that we have data for. I think they're thinking about getting 2016, but they don't have it yet. That would involve another outlay of money from them. And the majority of it, again, is either this enrollment information, which attempts to get at some of the complexity that Jeff was just asking about. So the complexity of when people are covered and exactly what kind of coverage they have, which is relevant for some people, but often not that relevant for many research questions. And then what's almost always relevant for everyone is this O row here, the O file information, which documents every single visit that everyone in the data set ever has with a provider. So this is, again, 14 billion records, 3.4 terabytes of SAS files. And I said a little bit earlier about the license and the opportunity now for researchers to get access to this data. So I'm hesitant ever to say that any data is big, because there's always someone who will come along and say that my data are bigger. And I'm sure there's people on campus doing, I know people doing astronomy and materials science research that generate a couple orders of magnitude more than this amount of data. But within this scope, it's decently large data. Okay, so what's this all about in terms of the tools and technology dimension of this? Well, as I mentioned earlier, there's actually been a small community of people on campus doing claims data analysis for many years, and they kind of flew under the radar. And they invariably and always use SAS. So the files are delivered to you in SAS format, and all the analysts use SAS format. Even some of the national standards on how to do things are actually explicitly defined through SAS code rather than through abstractions of what's intended to be done. So it's starting to look a little bit creaky to be approaching things that way at this point in time. There's nothing particularly wrong with SAS, and I'm not here to trash SAS, but it would be nice to have options. And so the main reason I was interested in getting involved with this, rather than trying to pass it off onto someone else who works at the consulting center, was because I wanted to undertake the challenge of performing a large-scale claims analysis without SAS, and I was willing to do whatever it took to make that happen. And long story short, that's why it took 3 years instead of 3 months. Because if I had just simply used SAS, I can sort of program in SAS. I probably could have done it in 3 months. And I could have borrowed a lot of code that's out there for doing things that people routinely do. But I just didn't want to do that. I wanted to see if we could have a path forward using modern languages, modern computing infrastructure, and simply avoid using SAS, obviously with a priority or a preference for open source where possible. So when I first started looking into this, and this was a couple of years ago, I talked to people who are big in the sort of HPC, big data area, and you, of course, hear people telling you that, of course, there's one and only one way to do this. You've got to use Spark. Other people will tell you there's one and only one way to do this. You've got to use Impala or Hadoop. Everyone has their tool of choice. And what they were really thinking was that you would use one of these data science-y type of tools like Spark or Hadoop to do the data management, to construct these time log files like I referred to earlier. And then once you've got it distilled down to something a little bit more manageable, maybe a couple of million rows, then you can easily load it into R Python or Stata or whatever and do your statistical analysis. And that would be a very reasonable way to proceed. But instead, I went a different route. So what I wanted to do was to see, there's a language called Go that I've been using in some other projects, some sequence analysis projects, and I kind of like it, so I wanted to see if we couldn't come up with an alternative approach here using Go, which is a very good language for maximally exploiting the capabilities of a single server. So it's not like Spark, Hadoop, and Impala, which are very much about chaining together a bunch of servers in a network and a sort of cloud distributed type of approach. Go can be used in that way, but it's more, in my way of using it, it's more about getting the most out of a single node. So nothing here, in my opinion, should really need 100 nodes to be accomplished in a reasonable amount of time. So what I wanted to do is to see if we couldn't develop some tools in Go to make this work on one node. So I don't want this to turn into an advertisement for Go, and I could have used C++ or Rust or some other languages that you may or may not have heard of. Go is just one choice that I happened to go with because I was already sort of familiar with it. But let me just spend about 30 seconds at most talking about Go, and then I want to move on from that. So Go is a language that was developed within Google to solve problems that they had on a number of fronts, including managing data centers, but also manipulating large data sets. So if it can manipulate Google-sized data sets, then maybe it is actually relevant here, even though no one else is using it. It's relatively new. They first started to talk about it around 2007, but it became a real thing around 2012. You can go to YouTube and watch some nice talks by the guy Rob Pike, who was the main person behind it at Google, who's also a big figure in the history of computing. He was around when C was developed. He was around when Unix was developed. He's the main figure behind Unicode. So he certainly has some credibility, at least, in this area. The reason that I'm interested in Go, and this actually connects a little bit with something I was chatting with Jeff about earlier, is that Go is supposedly like it's a general purpose language, but it's at a lower level than what you typically think of as general purpose languages. So it's a compiled, statically typed language, unlike scripting languages like Python and Perl and R and so on, which are very dynamic. So in that sense, it kind of splits the difference between C and Python, and potentially obviates the need for these scripting languages to always have like a two-pronged strategy in which you have a bunch of C code and then some kind of linkage between the C code, and then you have a scripting language up on top. So we were just talking about that. Cython in the case of Cython, or RCPP in the case of R. MATLAB has a way of doing this as well. So Go is a low enough language that you can potentially implement your intensive, tight algorithms in Go itself, but at the same time it's high enough that you can use it also for all of your scripting purposes. And so whether you think that's a good thing or not, that's a matter of judgment perhaps. But I've personally been frustrated with the way Cython creates sort of mangled C and obfuscates the underlying structure of what you're doing. So I was sort of interested in the possibility of working around that. I actually tried to do this whole project in Python to begin with, and it just sort of ground to a halt, crunching through the 3.4 terabytes of SAS files. Okay, so let me get a little more specific now in terms of what we've done. This is just over the last year or so. So there's three tasks we've sort of embarked upon here to make these projects capable of being done entirely in this setting. One has to do with data layout optimization, so I'll focus more on that. One has to do with data stream processing, and then the last one is about the actual statistical methods themselves. And I just want to emphasize that everything we've done here I would consider to be a sort of a prototype or like an alpha or pre-alpha level of completion in terms of the utility of the code for other projects, caveat emptor. It is pretty heavily tested, and we've used it in these projects, and we've double-checked some of the results against other systems where it's practical to do so. So I'm not lacking confidence about the accuracy of the scientific results we've produced using these tools so far, but I'm not making any claims about their ability to solve your problems. It's more of an experiment. I'm honestly not even 100% sure if we're going to, invest time in supporting these moving forward, or if this is going to be a learning experience and then we'll take something away from it and move on in a different direction. Okay, so task one, like I said, data layout optimization. So this is about getting the data out of these giant SAS files and into some sort of format that you can manipulate more conveniently, either potentially in SAS, but more to the point outside of SAS. And this is not Go specific. What we want to do here is we want to produce some data files that are sitting on the disk in a documented format, and then could be read potentially into Python or R or any other language using standards for standards for data structures that are in many ways language agnostic. So the way we approached this was heavily inspired by this project in the Python universe called bcults, which isn't very well known, but it's somewhat well known. So basically, bcults does a number of things, but what it does that was appealing to me and relevant here is that it defines a disk layout for native formatted data, which essentially takes large data sets, columnizes them, so organizes them by columns, and then dumps them into separate files by column. And there's more to it than that. I'll get to it in a minute, in such a way that you can then scan through the data very efficiently. So specifically what we do here is we have, again, column-wise storage. We want to pre-sort the data to enable high levels of run length compression and to make it fast to read through the data and to do a so-called full table scan. So most of the analytics that I need to do on these claims data sets is not like a querying sort of thing where you would just cherry pick tiny bits of data. You pretty much need to run through the whole data set to accumulate population statistics that show up, like, say, in the denominator of a weighted mean or something like that. So we basically need to plan for doing full table scans. It's not like one of these things where you'll never need to read the data from top to bottom. The other 2 points here will probably be more clear when I say in more specific terms what we did. So what this bcults inspired layout actually looks like in practice, and this is adapted to the market scan data, because the market scan data has this feature that the data is organized by type. So these A, O, S, F, I, D, L, and so on files, they're not really capable of being merge directly because a row in one file corresponds to something different from a row in another file. So we have to actually have 7 sort of parallel data sets and then sort of lightly merge them on the fly when we need to. So what actually ends up happening here is we do what people commonly call bucketing, which is we partition the data set into, in our case, 100 buckets based on subject ID. So you end up in some bucket based on your ID, and all of your data will end up in that bucket number. So for example, if I get bucketed to bucket 47 for my A files, then my I information, my O information, my S and F will also all get sent to bucket 47. That basically reduces the data by a factor of 100 per bucket. And then we can then use 12 or 16 or however many cores we have on the machine to crank through those buckets in parallel. So that's what makes it quite fast to work with this data once we get it in this format. If I didn't mention this already, I don't think I did, is that the SAS files are in a particularly unfavorable format for data analysis. Not just being in the SAS 7B DAT format itself, which I could go on and on about, but I won't. But also because the data they're not really sorted. They seem to be ordered by calendar time. So basically for 2009, you just have like all the January 1st encounters, all the January 2nd encounters, and so on. They're not all sorted that way. Some of them just seem to be not sorted at all. That might be useful if you were doing sort of like facility-oriented research, like you wanted to look at the pattern of consumption of surgical supplies, or like whether people get more bypasses on Thursday or something like that. That would be potentially interesting to some people. But most of the people I know, want to do a patient-oriented research. So what you need to do is you need to restructure the data so that all the information about one patient is sort of adjacent in the file, because you can't be jumping around these giant files, picking bits and pieces of data around. You want to do that once up front, because then this data is more or less static. They append another year on each year if they choose to buy another year's worth of data, but in general it doesn't change. No one's going to go back and edit this data. It's a fixed when you get it. So you put some work in up front to restructuring the data so that it's organized in the way that's most favorable for patient-oriented research, which is what most people are doing. And then you can just keep benefiting from that. It'll pay off in dividends as more and more people use the data, we hope. So, so the feature 1 is the bucketing. Feature 2 is the use of native types. And feature 3 is the sorting. And these things kind of interact with each other in positive ways. So and the columnization, right? So basically what happens is, say in bucket 0, file type A, there's something like 20 columns in those SAS files, and you create a separate file for everyone, for every column of that file, but only for the people who are assigned to bucket 0 based on their enrollee ID. And so these files turn out to be highly compressible because you'll have many rows per person, because again, A, if you recall, is the file that contains information about your plan type, like what you have covered. And so you end up having many rows per person because people's plans, the details of the plan are constantly changing. So you might have hundreds of rows per person, and so like their date of birth won't change, so that you have a run of 100 or 200 copies of the same value. So a very simple run length encoder will immediately collapse that down to one number times the number of times it's repeated. And so you get many-fold compression. Like in this file, you get like 100-fold plus compression because of that very high degree of run length coding. And even in fields that are changing, like the date changes. This is the date in this case when the plan type changed. Even the date changes every time, but these are still highly compressible because there's still regularities that a good compressor can exploit. So as we'll see in a minute, we were able to compress the data by a factor of 6. I think it's more like 10 actually. I say 6 in the slide, but it's really more like 10 over the SAS files without losing any information. So all the information is still there, but it's just represented in a different format that is 1/10 the size. And it's not so much about saving disk space. Disk space is relatively cheap. But if you reduce the data by a factor of 10, the data volume by a factor of 10, and then you need to scan through it, which like I said before is something we often have to do, then you spend 1/10 the time waiting for disk reads, which is actually a dominant factor in the overall computational time if you're doing something simple like just accumulating summary statistics. There's actually a bunch of tricks here, and it gets even more detailed than I think I want to get into in a talk. But just to throw out one more example, like I mentioned before, that in the claims data sets, a lot of the data are coded, and so like ICD codes are codes that there's this library or dictionary that tells you what all the codes mean, and you can use an adaptive coding scheme called uvarInt, which is used in Google's protocol buffers, if you've ever heard of protocol buffers. So a lot of the stuff we use comes out of that world. And basically what it does is it can use either 1, 2, 3, 4, however many bytes it needs to represent a code, but it jimmies things so that it uses the 1-byte representations for the most common codes, the 2-byte representations for the next most common codes, and so on. And that ends up being and so you can pre-calculate the frequency table for the codes, and you can get very high compression by using that type of var for variable width, integer coding for coded values. And because these data sets are heavily consisting of coded values, that actually turns out to pay pretty big dividends. We have general purpose software for doing this. So if you have a bunch of SAS files and you want to convert them, it's not just for market scan. For example, we intended from the beginning that this code we write would be applicable to Optum as well as market scan. We actually haven't gotten around to running it on Optum yet. I just don't have the time to do it right now, but that'll happen sometime in the next couple of months. So any other setting where you have roughly the same structure, where you have like large numbers of files and you want to use this scheme like bucket them, sort things. I think any kind of health record data, not just market scan and Optum, this could be used. So there's lots of tricks in the coding, but long story short, the time that it takes to create this data layout isn't that important because you only have to do it once. But just so you know, it takes about 24 hours on one node to crunch through the 13 or the 3.4 terabytes of SAS files and distill it down into this 600 gigabytes of structured information that can then be processed efficiently using other tools that we have written. And it's those other tools I'm going to turn to next. Those are the URLs. I think you guys have they have access to these slides, right, Alex or Marcy? Anyway,
I can send them out.
Yeah, or you can email me. Feel free to email me if you want to find these things and you have trouble. I'm not necessarily. This is more of a research talk. I'm telling you what we did and what we learned from doing it and what we were able to achieve and a little bit about some of the difficulties we encountered. But if you think these tools might be useful for you, I'd be very happy for other people to try them out. Okay, so the second task that we focused on, once we've got the data distilled down into that so-called layout, is to develop some stream processing algorithms. So stream processing as a strategy for data processing is nothing new. There are a variety of tools out there that treat data like streams. For example, the one that I was inspired by the most here is this Python thing called tools. I think there's a version of it called C-tools. The idea of stream processing basically is that you have something like an abstraction that's capable of reading data from a source and then feeding it to you, element by element. And most of these things have a common underlying strategy is that you have low-level primitive transformers that operate on these streams, and then you chain these primitive things together to produce very complex behaviors. It's a different way of looking at data processing and data management than the more conventional notion that you read the entire data set into memory at once in the form of something like a data frame, whether it's a Python pandas data frame or an R data frame. The point is the same. You're thinking always of this static rectangle of data in memory. In this case, you're thinking of a dynamic flowing channel of data passing through a bunch of actors, right? And this even goes back, I think another precedent for this is even very early in the history of Unix, is that a lot of the Unix utilities are designed to be piped together, so you can do very complicated things even with a relatively limited set of primitives. So there's nothing particularly new in the notion of stream-oriented processing, but I haven't seen it developed at a very high level for forming a bridge between big data sets like the claims data set and then statistical tools, which is the third of the 3 tasks that I'm going to try to squeeze into this talk today. The other challenge that we encounter here is that it turns out to be non-trivial to implement stream-based utilities in Go, because Go, I mentioned before, is a statically typed language. So you want to avoid, and it doesn't support, like if you're familiar with C++ templates and things like that, it doesn't support that notion of generic coding. So you have to do some pretty tricky things to avoid having to re-implement every function 20 times to be able to handle 20 different numeric data types. Well, there aren't 20 different numeric data types, but there are a lot. So we dealt with that, and I won't bore you with the gory details. This is an example of what our DStream package does. This is actually from that transportation project, just because I had a better looking example from that project. So don't worry about what the variables mean here, but this is just an example of how you would use it. And we use this to calculate Elixhauser scores for our health services research. We use it for defining these time logs in which when we do a lot of recurrent events analysis, so people who have cirrhosis have spells in which the comorbidities get worse and then they get better. These streaming type tools turned out to be very useful anytime you have like recurrent events and you want to do things like calculate the time delays or the time gaps between successive occurrences of a given complication. But anyway, this is in a different setting. This is in the setting of transportation research, which is another thing I have going on right now. And it's not, again, the point is not that you understand what each row does, but just the high level. You start with a source of data. In this case, it's a CSV file, but your source could be lots of other things. You define how to get the data out of that source, so sort of initialize a stream by connecting it to this data source. And then, like I said, you pass it through a sequence of transformers. So this stream object here gets created, and then it gets fed into a transformer, and then something new comes out the other side, but we just reuse that variable to hold the new thing, because we never need to refer to the old thing again. Again, it's embedded inside of this effectively. And then again, in and out, in and out, in and out, in and out. So by chaining like 7 or 8 primitive functions together, we can create quite complex behavior. Like most stream-based data processing tools, it has some properties. It's lazy, which means that basically nothing, let me go back one slide. When I first set this thing up, nothing actually happens, right? So until I actually start computing against this data, this is just sort of an abstraction. It's just sitting there waiting to be used. And it's only when you start pulling data out the end that triggers behind the scenes all of these transformations to start churning away, and eventually you reach the source and it starts pulling data off the disk, and then things kind of unwind in the other way. So that turns out to be a good thing, because if you actually don't end up using certain data elements in your calculations, they'll actually never be read, never be processed. So it's sort of efficient in that way. Let's see here. I'm almost out of time. So I mentioned a minute ago we use this one sort of basic task that we use this streaming calculation for is the Alex-Hauser score calculation. So Alex-Hauser score, as you may know, is a common way to summarize people's health status in one number. They have all kinds of limitations as a tool for doing that, but they are still useful. When you want to just include like a control in a regression model for someone's overall health status, you often want to include the Alex-Hauser score. They're a little bit tricky to calculate. So roughly speaking, how they work is you've got 30 different categories like heart disease, cancer, psychiatric illness, and so on. And it's just binary. Within each of those categories, you may or may not have that condition, and then you add up the numbers. So in theory, your Alex-Hauser score can be anywhere from 0 to 30, although for almost everyone, they're between like 2 and 8. So the challenge here is that there's dozens, and if not hundreds, of codes that define each of these categories, and these codes can appear in different files. They can occur, remember, they can occur in an outpatient visit, they can occur in an inpatient visit, so they might show up in the O files, they might show up in the I files, they might even show up in these service visits or in the lab data. So we have to sort of stream through in parallel all of these different sources of data, check for the codes, and as soon as we see a code for the first time for a given person, we add one to their Alex-Hauser score. At a high level, that's something that should sort of feel like something that can be calculated very efficiently in a streaming manner. And so I'm using this as an example of a calculation in health services research that is very well adapted to the streaming style calculation. You never hold more than, say, 10 or 20 patients' data in memory at once, so it's extremely memory, minimal in terms of its memory demands. And if I didn't say this before, we can actually stream through this large data set, calculate Alex-Hauser scores for everyone in the data set in like less than 10 minutes, 5 to 10 minutes, depending on the details of, there's some options in terms of exactly how you calculate the scores. So I think that's fairly impressive. Now, if someone told me that with Spark you could probably do it in 1 minute, but then you're using 100 machines. So this is on one machine, you can do it in 10 minutes. I'm willing to wait 10 minutes. And just to kind of close the loop here, we have the final step of what I normally need to do is then finally you need to take the data once you've restructured it as streams and actually run it through statistical models. So this could be anything from like a survival analysis model to a generalized linear model, least squares regression, often with lots of ancillary stuff floating around the edges. We almost always have weights, we almost always have stratification, we usually have some form of matching, we often have like some kind of propensity adjustment going on. So we need, at least if you want to do this all kind of in a unified way, we need tools to fit these models and that are capable of supporting all the things that I just mentioned, all the ancillary things that I just mentioned. So we have worked over the last year or so to implement what I would consider to be the bare minimum of core statistical methodology that's used in health services research, all of the things that I just mentioned and a few others. And these are actually engineered and optimized to accept data out of these streams. So that's there's no conversion, there's no data type conversion, there's no sort of format conversions that need to take place. The least squares regression or the Cox model or whatever it is you're fitting, it just pulls the data right out of the stream and immediately starts cranking away at it. And especially for methods that are like one-pass methods, these are cool. You can fit certain types of models on data, never like just making a single sweep through the data. For the methods that require, like Cox modeling requires usually like 7 or 8 passes through the data to converge. It's a little bit awkward because you've got to restream the data 7 or 8 times. So in that case, it really only works well for data that can fit in memory once you distill down to the amount of data that you need to run to fit a Cox model to. But other things we can, like the Elixhauser scores, we can calculate on the whole data set. Okay, so I think I'm out of time, right? All right. So that's just an overview of what we've been doing, and happy to take questions or.
Yes.
So, are there summary statistics or anything calculated on the overall population data that you can use to kind of compare what you pulled out to see, like, is it biased in this way or that way?
In terms of accuracy, is that what you mean?
Or just seeing how it's, if it's skewed towards, I don't know, older patients or, any of it.
Well, I think I get it what you're saying. So what we know that MarketScan is not unbiased. They don't claim to be unbiased. What they claim is that it's representative enough that you can then use weights to adjust for the biases. So the way that works is that we use a survey, either MEPS or the ACS. So ACS is a famous survey, but MEPS is Medical Expenditure Panel Survey, which is a government-run survey which is normed against the census and therefore is supposedly representative of the U.S. population and can be used to subset. You can also use it to target subpopulations like the ESI population. So what we do when we need to make those population projections is we take MarketScan, we divide it up into strata based on demographic variables, and there's all kinds of debate about the right way to do this. You calculate the MarketScan size per stratum, the population size per stratum based on maps, which is considered to be very accurate, and that gives you weight that you use to adjust up. So I'm not sure if is that sort of responsive to your question?
Basically. So even the whole entire data set is not good enough for normalizing.
Neither MarketScan nor OptimInsight are they're both convenience samples. Neither one of them is representative just as a unweighted collection of data.
Weights and correct.
I didn't mention this. It contains around 1/3 of the population, so that's a big subset. But even a large subset of a population can be biased. So we know, for example, that we undercover in MarketScan. There's more like urban coverage of urban areas than like rural areas. There's more coverage of certain parts of the country. But and this is a great research topic. I would like to get into this more myself. I just haven't had time to really evaluate the extent to which you really are doing an honest population projection from either Optim or MarketScan, because many people are claiming to do so. And whether they actually are or not, I think would require a lot of work. But at the minimum, we've used this standard weighting technique to adjust for what could potentially be obvious biases.
How much do you worry about? How confident are you that that's doing a good job?
And that's why I say that I think this needs to be looked at more carefully.
Okay.
I mean, we're not claiming that this can project outside of ESI. I mean, it's clearly limited to ESI. And I don't know. Let's see. The only thing that we worry about with MarketScan a little bit is that we know that their client base is larger employers. So we're getting larger employers rather than mid-sized and smaller employers. Well, very small employers typically don't provide this type of coverage to their employees anyway. But we know we're missing like the companies with like say 30 to 50 employees, because MarketScan I think starts at companies with 100 and up. So if there's some like sociological or demographic or health difference between people who work for medium-sized countries and larger companies, which there could be, then they're subject to these biases. And the weights may partly help with that, but they probably don't completely remove it.
When you first get the data in there, is there like a laundry list of QC measures that you run it through to check things?
It's not so much that, I mean, we don't have, so if there are errors in the data, I'm not sure how we would even know that. We don't have, I mean, I don't think the data have been cleaned to the point that the obvious logical inconsistencies should be gone. So I'm not sure that there's any way to do that. Or did you have something in mind about how to check?
No.
I mean, if someone was born in 300 BC, that would be something. But I think those things have been vetted. I mean, this is not like ultra raw data. Part of the service
I was thinking a little bit more complicated things than just the coding error.
Yeah, I mean, there could be people who have combination of diseases that like would almost never happen, but in the population as a whole, you can't necessarily say that it didn't happen once. Yeah, it's everyone accepts that there's lots of errors in these data, and some of those errors can possibly be rectified by, like I said, like we won't just say that someone has a condition just because they have one code for that condition. We usually would require them to have like either multiple codes, or they would have the code for the condition, and then they would get treated in a way that would be consistent with them having that condition. The more, Tianqi Kai from Harvard was here last year, and she gave a very nice talk about her work in this area. The more sort of hard to diagnose the condition is, so she works largely on rheumatoid arthritis, the bigger a problem this is. Like someone with a rheumatoid arthritis code, with one rheumatoid arthritis code, they only have like a 50% chance of actually having it, according to like standard diagnostic criteria. Because doctors will just enter a code like that for someone who says like my wrist hurts or whatever. For cirrhosis, you would hope that they're not just entering, that's a serious condition. You would hope they're not just entering that code freely. But I'm sure there are borderline cases where someone has another liver disease and it shows up as cirrhosis and that was the wrong call.
Yeah, there's probably some codes that doctors fall back on because they know that the insurance will pay for it if they use that code. I've even had my doctor tell me, like, well, I could bill this as this, but it might not get covered, so I'm going to bill it as this instead.
Yep.
Okay.
We know that happens. We know that happens. And we're mainly interested in the disease and then the major comorbidities, and we would hope that that wouldn't be something that would be entered in erroneously. Yeah.
So far, what is the most powerful predictive variable among all this data, and what's the most predictable disease?
Well, we're not looking across the spectrum at many different diseases, and this isn't primarily a prediction-oriented project. So I have just getting started now. I have a new project looking at heart failure prediction. So then that's very much in that spirit. Like you want to look at, given what you know about a patient right now, can you predict whether they'll have heart failure within 2 years? That's very much a prediction-oriented project. The cirrhosis stuff just wasn't brought to me as that type of a question. So the main goal of the cirrhosis project was almost more epidemiological in the sense that they wanted to rigorously quantify the burden of cirrhosis, so cirrhosis is a disease that it's complicated. It's caught up with all kinds of trends about like, the rural white populations and opioid abuse and unemployment trends in certain parts of the country. It's associated with lifestyle things like heavy drinking and drug abuse and so on. So there's a widespread belief that cirrhosis as a chronic disease is increasing in prevalence, but there actually wasn't a lot of data to document that in the general population. Certainly in the VA and the CMS Medicare populations, that's been well established, but it's harder to do that kind of epidemiologic work in these populations for many of the reasons that I hopefully came through today in my talk. So this is the first, as far as we know, like really rigorous documentation providing evidence that cirrhosis is increasing and the rate at which it's increasing, which is not exponential, fortunately, but it's fast enough that there's going to be, it's expensive disease to treat. So there's going to be an increasing burden on the gastroenterologists and on the medical practices that have to deal with this disease moving forward because of the increasing trends. So it was more of a statistical epidemiological goal here rather than a predictive aim.
Excuse me.
Yeah.
I'm just curious, do you have plan to extend the usage of these tools to other kind of data besides electronic health records data?
Well, we're already using, so there are 3 things here. There was the data layout, the SAS file crunching and part of it. There was the streaming part of it, which we're already using for transportation data. So the answer to your question is yes for that. And then the third task, as I referred to it, is broadly just implementing various statistical methods. And so there's nothing EHS, health research specific about survival analysis. People use that in all kinds of domains. But the first thing is probably, it would be useful mainly for like administrative data about people, not just necessarily health data if you had data on crimes or educational data or something like that, but it kind of works for data that's indexed by person and then by date. So if you have many events per person indexed by date, any data set like that, the first tool could be used in that setting.
Any last questions? Okay, thank you.
Okay, thank you.